All right, so this is going to be the video for topic 9.1, or 9.10, I really should say. Yes, we're going out of order. I felt like this was a topic that you could easily handle through the video compared to the other topic that we have remaining for this unit. And so we're going back to a little bit of stoichiometry and a little bit of mole conversions. You're going to need a calculator, your periodic table to get started. So the first thing we're going to look at is molar volume. So way back when we first started and introduced the mole, we drew this map, if you recall. And when we drew this map, we had mole as our center town. And then we had these two other parts. We had particles and we had mass. And so those were the only two parts of the map that we included. And mass, if you recall, is in the unit grams. Particles can be things like atoms and molecules. And the third one being formula units. So today we're going to add the third leg to this map, and that is volume. Volume is going to be related in the unit liters. And so we're just doing conversions. We've done conversions all year. And so where it comes from is Avogadro found that when a gas is at STP, you have to recall that this only applies at STP, and that's standard temperature and pressure. So at 0 degrees Celsius or 273 Kelvin, 1 atmosphere, 760 millimeters of mercury, so on and so forth, this is true. And he being Avogadro, found that 1 mole of any gas, so helium gas, hydrogen gas, oxygen gas, carbon dioxide, sulfur hexafluoride, any gas will have the same volume at STP. All gases, no matter the composition, occupy 22.4 liters. What he developed from that is a conversion factor we refer to as molar volume, that 1 mole is to 22.4 liters. So to look at the couple examples I have working with this conversion factor, in the very first one, it asks us to calculate the volume that 4.5 moles of hydrogen gas at STP will occupy. So we have our given of 4.50 moles. And I'm going to go ahead and include by formula. So this is hydrogen. Hydrogen is Hoffenkleiber, so it is H2. Remember, what the map did for us is it helped determine the number of steps needed to complete a conversion. So I can see that I'm starting at moles and I want to end in volume, volume being a liter. So that is a 1-step conversion using our new conversion factor. My given unit being moles means I need to divide by 1 mole, multiply by the 22.4 liters, and we're ready to solve. When it comes to our answer, we're going to keep 3 sig figs from our given. And so with rounding, we get 101 liters of hydrogen gas. You can cross out the moles here if you would like, and then we're all done. So in number 2, it asks how many grams of carbon dioxide are in a 1 liter balloon at STP. So here I can see that I'm starting at volume because my given unit is the liters, and it wants to know grams, which is mass. There is no direct conversion, so remember we go to moles and then we can go out to mass. So what we'll start with is our given of 1 liter, and it's CO2 because it's carbon dioxide. And the very first thing is I need to get from liters to moles using molar volume. Same setup, or excuse me, not the same setup, but same conversion factor. 1 mole is going to be the top, 22.4 liters is the bottom. Again, I can cancel my liters. I'm now at mole. I need to get to mass, and to do that from mass to mole, we need molar mass. If you recall, carbon dioxide, CO2, so we just use the mass of 1 carbon being 12.01, 2 oxygens, each with a mass of 16, so 32, combining that together for a total molar mass of 44.02 grams. Again, numerous ways to solve I'm going to take 1 divided by 22.4 times 44.02. I can keep 2 sig figs from my given, and I get an answer of approximately 2 grams of CO2. So again, we've done numerous conversions going between these earlier on this semester. The only thing that's new is this piece here. And last but not least, the last example here is if I have 1.2 times 10 to the 24th molecules, remember we can abbreviate that as MQL, of nitrogen gas, so N2, how many liters does it contain? So again, I can see my given is molecules, which is a particle, and we want to know volume. No direct conversion, so it's a 2-step. We have to get to moles to get to volume. So it's been a little while since we've used this number, but if you recall, the number we use is Avogadro's constant to go from molecules to moles. That is the 6.022 times 10 to the 23rd MQs, and that's per 1 mole. That'll be my numerator. It wants liters, so I need to get to volume. Because I have molecules canceled, I have mole in the top. 1 mole will be my denominator. 22.4 liters will be my numerator. And I'm all set to solve. Don't forget to use the EE function for putting in your scientific notations here. If you run that through correctly on your calculator, I got an answer of 44.6. And that is going to be liters of nitrogen. Okay, so that's the first part that we're working on today. The second part is tying in gas stoichiometry. So let me scoop my paper. So in our next part, what we're going to work on is how to do stoichiometry using gases. And so if you recall, a coefficient in a chemical equation, once it's balanced, can indicate moles. So we used a mole ratio back in our Stoich unit. And now we can basically do that same thing, but instead of using the unit mole, we can use liters for volume. And so this only works if things are gases. So propane, C3H8, is a gas that is sometimes used in as a fuel for cooking and heating. Complete the combustion of propane using the equation below. So again, you need a balanced equation in order to do anything else. Hopefully you recognize this as a combustion reaction and that you should start with carbon. The other trick is this is an odd number, so we don't have to put a 2 in front, so we can leave it as is with the 1. So I'm going to place a 3 here in front of my carbon dioxide. I have 8 hydrogen on the reactant side, so I'm going to place a 4 on the product side. 3 times 2 is 6. 4 times 1 is 4. 6 plus 4 is 10. So 5 times 2 gives me 10, and that's balanced. Now, the one thing I included is if you take a look in all of this reaction, when you go through combustion here, all of these are in the phase of being a gas. So this makes this conversion for B and C really, really easy to work with. Again, this applies only if things are in a gas to start and end with. Here it asks what will be the volume in liters of oxygen for the complete combustion of 0.35 liters of propane. So what we have here is we have 0.350 liters of C3H8. Like what we did in Stoich, we did mole-to-mole conversions where we got our mole ratio from our balanced equation. Because we're starting with a gas and converting it to another gas using coefficients, we can say instead of moles that these are liters. So we can complete this conversion in one step using our coefficients to make, instead of a mole ratio, a volume ratio. So how that sets up is because we are given liters of propane, the ratio here is that this is 1 liter of propane, so 1 L of C3H8, and we're changing it to liters of oxygen, the coefficient there being 5. So it's a 5-to-1 ratio. And all that's necessary then is multiplication to then get your answer. So when I multiplied that out, I got an answer of 1.75 liters of oxygen. Now in letter C, we want to figure out how much CO2 would be produced. You can have two different givens here. You could start with either the 0.35 or you could start with the 1.75. Either one is okay to use. It's just based on your preference. I'm going to just use the 0.35. So I'm going to use 0.35 liters of C3H8. What I'll find is that the denominator is the same because the coefficient is the same. So this is 1 liter of C3H8 is to 3 liters of CO2. So like before, all I need to do is multiply, in this case, multiply by 3 instead of 5, and I get an answer of 1.05 liters of CO2. So again, these are one-step problems when you're going from a gas to a gas. And so this is a liter to liter conversion, okay? And they both have to be in the gaseous state. Now there's two remaining examples that show some different options of how you can work with this conversion along with the conversion we did up above. So here we have quicklime. Calcium oxide is produced by the thermal decomposition of calcium carbonate. Calculate the volume of carbon dioxide at STP, standard temperature and pressure, produced for the decomposition of 152 grams of calcium carbonate by this reaction. You always need to start with a balanced reaction. Well, we have 1 calcium, so those are balanced. 1 carbon, 3 oxygens. Well, I have 1 and 2 there total, so it's already balanced. You can leave it blank or write in a 1. So what we're trying to do is we're starting with 152 grams of this calcium carbonate. Where we want to end is how many liters, because it's asking for volume of carbon dioxide. So we're looking at, if we start with this much reactant, how much of this product will we produce? So the first thing I can see is with my given is that I have 152 grams of this CaCO3. Well, if you think about it, the first thing we did all through our stoichiometry unit is if you start with grams, the only way you can get rid of grams is through using molar mass. So again, you would add up 1 calcium, 1 carbon, and 3 oxygen. When I did that, I got an answer of 100.09 is for 1 mole of calcium carbonate. Once your grams have canceled, this is like a mass to mass conversion. However, we're going mass to liters. The process is going to end up being the same number of steps. The next step is going to be your mole ratio. And so this is going to have to be a mole ratio, not a liter ratio, because the calcium carbonate is in the solid state here, not a gas. You can only use the ratios when they're both in the gaseous state, which it was not, unlike the previous side. So if we look, it's a 1-to-1 ratio. So for every 1 mole of CaCO3, we have 1 mole of the, carbon dioxide made. Okay. If I keep track of my units, moles now cancels, and I'm now at the answer of unit of moles now of carbon dioxide. I'm not done. The problem specified that it wants volume. We know how to convert moles to a volume, moles to liters. That's using our molar volume conversion factor, that 1 mole is to 22.4 liters. Moles cancels. I'm now at liters of CO2. Again, make sure you're careful with how you run this through on your calculator. If you work everything out correctly and keeping 3 sig figs, we get an answer of 34.0, and this is liters of CO2. So again, the reason why we couldn't do it in one step like we did on the front side is on the front side, we were going from liters and we were ending at liters. Everything was in the gaseous state. Here, we started with grams, and then we could not just use a volume ratio here because it's a solid that forms a gas. Okay. So the last one, you may want to pause the video real quick and see if you can work it out and compare how you did. So what we have here is a synthesis of table salt, sodium chloride, through sodium reacting with chlorine. My chlorine are not balanced, so 2 on the product side. We'll then require 2 on the reactant side for the sodium, and we're then balanced. Like the previous problem, number 1 up above, we have a given, and this is 4.81 grams of sodium metal, so just Na. And it wants to know how much in liters do we need of the chlorine gas for that all to be reacted. Like before, the only thing we can do here is change grams of sodium into moles of sodium because it is a solid and it's in the unit grams. So the molar mass of sodium, according to the periodic table, is 22.99 grams. Our next step, like this is a mass to mass conversion, was to get our ratio to figure out the proportion between the reactant sodium and the reactant chlorine. Because I'm currently in moles of sodium, I'm going to put that in my denominator. So the ratio is for every 2 moles of sodium, you need 1 mole of chlorine gas. Like before, because this problem is wanting volume, not moles, we have to change moles over to liters using molar volume. That 22.4 liters is to 1 mole. Double checking units, grams canceled, moles of sodium canceled, and the unit mole canceled. Again, making sure you're careful with how you run it through. With 3 sig figs, you should get an answer of 2.34 liters of chlorine. And that's how you work with stoichiometry and molar volume, applying it to gas laws.